last time we were talking about Euler characteristic formulas.
Okay. Start over. So last time I ended a little bit rushed toward the end. So let's sort of review that part of argument in a more detailed way, since we now have more time. So we're talking about a representation on F. Basically, we can reduce to the case where I can take an L containing mu L, and my representation M is the induced representation from this small h to G of a representation N, and L does not divide the order of H. That's sort of the setup. Then I wanted to compute chi of R gamma tuita in my notation SF GSM. So this is let's see, right? So this turns out you can reduce it essentially to I from 1 to 3 of minus 1 to the I dimension of FL of H tilde I SLF of GL SL mu L by the exactly same argument as before. So essentially you use the Shapiro lemma to reduce for this Galois multiplier F to L, and then you pull out the N outside. So inside you leave out a mu L, and over here you twist back the minus 1. Okay? And you want to show that whether that's equal to sort of sum of V and S infinity of dimension of FL of H0 of GFG induced representation. But that's the same thing as sum of W in S on K. Yeah. So, right, by the Shapiro lemma again, the dimension of, let me just write dimension without writing FL. So this is GFW of N. So you want to show these two are equal in some sense. Last time I guess I was bound by the notation, so let me introduce some notation. So for a, let me say, if you have a ZLH module map, let's say P goes to Q, then I can define such that kernel and co-kernel are killed by P. Oh, excuse me, killed by L. Then I want to define. I want to basically sort of write this expression here in some sense. So I want to write chi of N of P that goes to Q to be equal to the dimension of FL of kernel of this map tensor with N minus 1 H. So basically whatever I have over here, I just sort of talk about this sort of middle part here. So this is the middle part, which will be our P dash Q, either kernel or co-kernel of this thing. So I take this, and minus the dimension of the co-kernel of the map. And then I write chi n p to be sort of chi n. Where I put subscript n to mean that I take sort of h module n here, dependent here. Okay? So to just take this to be mapped to 0. So that when I write this, somehow notational-wise, this is a little bit better. Maybe let me note a couple of things. Is that if I have sort of chi n, and if sort of p is finite dimensional, or maybe not sort of finite length ZL module, or rather sort of finite Billing group, say, same thing. Then chi n of p goes to p. Whatever map you have is 0, because whatever the kernel and the co-kernel will have the same sort of Jordan-Holder factor with respect to the H action, and therefore they would sort of they will cancel each other. And also, this is for 1. Secondly, is that if P and Q are, I guess, finite free Z module. I mean, all of these, when I say that, they carry H action, okay? Such that if I tensor this with QL, they are the same as QL, QLH module. Then I guess I want to say that. So maybe I can. I guess when I do this, I only use the case where it's multiplication by L. Then these are the same. That's because somehow, like, you're talking about sort of a same QL representation of H. You're taking different lattices. At 2 different lattices, you can. I mean, you did this homework probably. So the 2 lattices can adjust into. They're just off by a multiple of p, and then essentially you just write down the Jordan-Holder factors, and that's how it's done. So I'm going to use these two sort of standard facts. Now, let's recall the following. Let's move on this side. Okay. So let's compute this somehow. We already did it, so let's recall the computation. So this H cubic I SL F of GL SL. The thing I want to take cohomology HI here. This is equal to the kernel of the map L cross it's the same thing. This is when I equals 1. And this is the co-kernel of the same map. I equals 2. Maybe I'll just write same. This is a little too long for me to write. And then it's FL if I equals 3. Okay? So that's something we've already computed. Let me leave this formula here for our later to check. Okay, let's move down here. So then we see that using the notation we have over there, I can rewrite this chi. This notation is a bit long. That's equal to sum of, no, not sum. Because I'm taking somehow the alternating sum of these things. I get, see. So I'm taking the kernel and co-kernel of this guy. So according to my notation, I'm getting minus chi n of this. I'm taking chi n of minus this one goes to multiplication by L to the same thing. Because the reason I have a negative sign here is because it started with I equals 1, and naturally here we have a negative sign here. Then I also have to take care of the I equals 3 term. So I have a negative chi n of FL. So those are the sort of two terms. So basically the H1 and H2 is combined in terms of my notation. This is some sort of chi n here. Then I'll play with this notation. And maybe let's just add one more. So if I have an exact sequence as so, then because see all the terms I care about are of this form, p by multiplication by p. So I can write chi n of p goes to multiplication by start with q. That's equal to chi n of p things. R. So when I have an exact sequence, this is additive. Right? This is sort of standard. Maybe before I erase, the reason this is additive is because taking H invariant is exact because my coefficient is L torsion and H has order relatively prime to L. So taking, I guess, H invariant is exact. So I have this. Otherwise, I would involve hierarchical homology of H. Okay. So now let's do the computation. So let's compute this guy here. Let's see. Now I want to use the following exact sequence. How should I put this? So let's put this thing in somewhere here. Product of V naught in SL O L V cross. Okay. So I can. First of all, throw in V in SL of OLB cross, but only those finite part. I guess we need a little bit more space here. I also need to throw it because I have a full SL, SL infinity of OL cross. I can throw this part into this. So that the quotient now becomes, if you take this map, and the quotient would become ALF cross. On this side, mod L cross. On the other side, mod all integral local terms. And that's precisely the definition of ideal class group of L, OL. Right? Whereas on the other side, the kernel is precisely OL cross. I mean, this you can see by instead throwing L cross into this quotient somehow. The intersection of L cross with this thing, with the integral part, is precisely OL cross. So we have this long exact sequence. And now I have sort of 3 term, I can extend to 4 term. That sort of works the same way. Now I can continue to write this thing. Let's see, maybe before that. do need an OL cross closure. Right. So let's see. Okay. So now I can continue on this equality. So I have, thank you for that comment. So let's see. So I have a negative of this, right? That's going to be equal to this. That's going to be equal to, let me just write down what I have. So that's going to be equal to this minus sum of V Archimedes place. So this is minus, so all the terms in these two are minuses, so chi of ideal class group of CL. And very end, I have minus chi n of FL. Okay? So I've listed all the terms. So essentially replacing this term here by other terms of the long exact sequence. And this is from left to right. And of course, there's at the end, there's a chi and FL here. So let's analyze these things. It's not that hard. So first of all, this, if I multiply by L, these are all C crosses. Because my L is complex. And therefore, hello? Very strange. What? Hello? Yeah. Hello? 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 I don't know. 我在考虑这件事吧。let's do this. 如果不录的话，我就用中文说。这边有不懂中are there? They all speak Chinese, right? Okay. 我录哎呦，那要录也是怎么办？真他妈烦。对，这个 sequence 是 invertible 随时上来一个。啊 ？Maybe it's okay. Okay, let's try. So this is C cross. Okay, this is C cross, and it's invertible, so this equals 0. I really don't record it. And this is finite. So as I said earlier, this is also 0. And this part here, so only when V divide L matters. Right? If V does not divide L, somehow the torsion part is finite, you don't have to care about. The non-torsion part is L divisible, in which L is invertible. That's okay. And if V divide L, we've discussed this before. So this is the same as dimension of FL. Or essentially, you take some exponential map here. So you have OL. Okay. Looks like OL, but then you want to replace O. Remember, you have LKF. Here you have extension or child group is H. So you want to replace it by OKH modulo FL, modulo L, and then cancel with N minus 1 and taking H invariant. And we talked about this, how you have a regular representation, it will X up any representation you have. So this will just simply give you simply the dimensions of N. Basically, this will cube all the sort of reasonable representation here. You can just think of it as a plain vector space N. And then we'll take H invariant it will kill the regular representation part here. So this will be equal to the dimension of n times the dimension of OK mod, or rather K over QL. Q. Okay. Okay. So that's a little strange, a little glitch of technology. Okay. So you have these. So these are all well understood. So now the last one here. Let's see. Yeah, then we can take L2 substance. No problem. The kernel, it has kernel. Good point. Okay. You're right. Sorry. Okay, it's my bad. I didn't realize this. That was embarrassing. So you have to do this. So you do get mu L, and then tensor with. Let's see. What do I get? So let's see what do I get? I get somehow a direct sum for all the places dividing infinity of L, that mu L, tensor with n minus 1 to the h, right? And so this is just sort of a direct sum of b dividing infinity of n. And together h. So let's leave it as is for now. Okay? I think this will combine well with it, one on top. What is it? But no. It's all like for L, it's all complex. Yeah. So because L contains mu L, so all the Archimedean places are complex for L. So we do have this term. Sorry, I miscomputed. I'm a little nervous about this term now. But let's see. We'll get through this. So for the other one, maybe I'll try to go back to white. I feel like this is a bit dark, this color. So let's recall how we did this. So we have OL. The way we analyze this is somehow we embed it into, there's a log map, right? So when we learn, how should I put this? When we learn, excuse me, right? So this goes to, I guess, for each embedding you have an R here, so log of this norm. And then you sum them up. Right? I mean, remember when we learned basic algebra number theory, the units will be mapped into taking the log of their embeddings. We'll map into a product of R's, and then they have the property that if you sum up all these the log of the absolute values, you get 0. And this will span, this OL will span the kernel of the thing here. And we also know that, of course, this I mean, up to a finite thing. Oh, okay. This is equal to mu L cross a z to the well, there's no R1 here. R2 minus 1. Right. So the structure-wise, this OL cross is some finite thing, which doesn't matter for my formalism, times some free thing. And if I multiply by L, I'll be seeing the co-kernel of the sort of free thing here. And so we know that somehow this will be the same thing as chi L of just some FL to the R2 minus 1, or rather, well, let me first write this and I'll change, okay? We know that it's going to look like this in terms of modules. But now I have to explain what the H action on this space is. So the H would act on this space here, right? The action of H will be translated into, when you do this map here, or translate into action on these factors here. So therefore, at the end of the day, what you see is that somehow this is the same as direct sum of V divided L of each one you put in FL. And then you put maps by the sum. You map to FL here. Right? Oh, so it's minus, huh? Oh, so closure. I mean, closure doesn't really matter. I mean, like, so if Z mod L, same thing as Z hat mod L. So closure doesn't really matter much. So you can basically, I understand I should be written closure, but somehow when I do the calculation, I don't have to think too much about the closure. So essentially, I'm doing Z mod L. So each of the lattice here, well, each of the thing will be kind of forming R basis of this space here. The H action on this space is given by the usual Galois action. So somehow the H will act on the embeddings here. So that's what I get. Right. And note that I'm taking a co-kernel of this one, so I get a negative sign here. I can separate these two out, so I get chi n of. Oh, so excuse me. This is the dimension of. So I get dimension of. M minus 1. To the H minus the dimension of. I'm losing numbers. I'm sensing this is not going to be correct. Sorry, so this is minus, so this is minus. My bad. So this is minus, so this is minus, and this should be sub plus. And when I wrote this is going to take a minus sign because of our minus sign here. This has a minus sign here. Similarly for this one, you have a minus sign here. And this will kill with this bit here. Now we're left with these terms. To apologize. I didn't see this coming. Sorry. I'm confused here. I'll do that next time. Just a tiny bit here, I can't figure it out. Sorry about that. I'm confused. Maybe I should. So maybe this bit here is a bit problematic. Maybe this shouldn't be here somehow. My understanding this should be 0. But I'll go back and check what happens here. How about that? I think this is not. Oh, sorry, this is not 0, but somehow whatever causes this term should be 0. I'm not so sure what happened here. Okay, so oh. Okay, sorry. So suppose I don't have this term. Doesn't matter. N can have some H invariance as well. And also the H will act on here as well. Sorry. We'll come back to this. I think there's something. The problem may not be here, so that's a bit annoying. So this is now for this I need to use a Shapiro lemma. So you're taking H invariant and H acts on all the Archimedean places. So now you can reduce it to V dividing N, but V is a place of K of H0 of G was KV of N minus 1. So because H acts on this one, so you can think of it as sort of induction from K to, so, I mean, right. So like that. So, yeah, I don't think I need to do much. So now we're left with two terms: this term and this term here. So basically, this term is equal to somehow the sum of this, where the n doesn't have the somehow the difference of these two terms is precisely what I want, I think. Sorry. Okay, I'll write you a note about this. I'm a little confused. Can't think. Sorry. I'm a little confused by this. Apologize for that. Okay, so now let's move on to a new topic. So let's talk about the deformation problem, deformation rings and stuff. So this would be a little bit easier than duality. So I always take E to be a finite extension of QL, and my notation will be these coefficients. These are the sort of O being the real integer, and bar pi being the uniformizer, and F being the quotient, and F a finite extension of FL. And this fixed G, a profinite group, satisfying the following conditions. Following equivalent conditions. First, for all finite length, module M with continuous G action H1 GM is finite. Secondly, you don't have to check for all such representations. It's enough to check, well, you don't have to check for all finite length representations, OG modules. It's enough to do the trivial one, but you allow yourself to work with covers of G. So for all open compact subgroups, H in G, H1, H, FL is finite. Okay. So it's I leave it as an exercise to check these two are equivalent. Okay. But this will be the setup we're going to consider. Let me also mention that there's a variant of this. You can replace 1 by I for any I, and replacing this 1 here in the same way for any I. Those two also equivalent. Okay? So only you can make the statement of equivalence only for H1 or for all HI. So these are all kind of equivalents. But what we really care about are the two examples we're going to consider. First is that if K is a local field, same thing. I allow myself allowing QL, but not serve the function field where L equals L, where L equals the coefficients. And then G equals GK, the Galois group of K. Or I'll consider F is a number field. And as a finite set of places. And G is a Galois group of the maximal extension of F, which is unramified outside S. Oh. Should be more careful here. So I want to talk about so-called Galois deformation. So let's talk about, one more concept before discussing what we want to do. So consider a category. Let me write CNLO here. This is the category of complete Noetherian local O algebras. So CNL stands for complete Noetherian local O algebras. So when I say local algebra, so I have a local ring A with this maximum ideal M, for which there's a small condition. The structure map homomorphism O to A. It means O algebra, so you have a O goes to A. And one that induces an isomorphism. Well, I guess I can probably just say A quotient by M is isomorphic to F. But I want to. That's good. So this is the category. And also I want to point out that somehow the morphism here are local maps. Namely, when you have A to B, you want to map f of MA into MB. Right. So now let's talk about what we want. So suppose that we're given a residual representation. I'm really thinking about G as a Galois group of one of these two kinds. So suppose I give myself such a representation, rho bar. I want to consider possible lifts in the following sense. I guess in my mind, I really want to lift it to GL and O such that, there's an obvious map from O down to F such that when you compose this is rho bar. So somehow you lifted rho bar homomorphism from G to GL and F to GL and O. But you want to, I guess somehow it's relatively easy to find one lift, but somehow it's better to find a kind of universal object that gives you all lifts at the same time. So you want a universal lift somehow. And others can just obtain from the universal one. So let's phrase this, what we want to do in terms of something that's more, I guess, concrete language. So I want to consider the following two functors. The first one I call depth for deformation, rho bar. I put a square here. This is called the frame deformation. You will see why it's called frame in a bit. So this sends a complete Noetherian local O algebra to all possible lifts. Continuous representation rho from G to GL and A such that if I do rho, I say, okay, mod MA or mod M, I guess. This is just equal to the rho bar given to me. Just like so, just like what I have over here, except I don't just talk about deforming to a just one O. I deform it to an arbitrary complete Noetherian local O algebra. Talk about all such possible deformations. And there's a variant without a square. Usually we call unframed. Well, the reason to talk about unframed deformation is because somehow, if you look at this, you say, okay, if I have a representation, if I conjugate a representation by something, it's really sort of the same representation. But the way I define it in the frame deformation is that I really want this I just talk about representations as matrix, maybe I should say continuous matrix representations. So if the two representations, they're conjugated by something, they're considered two different representations as far as the first one is concerned. So the second one, when I define it, I want to sort of consider two representations. If they're conjugate to each other, then I consider them the same thing. So that's the continuous representation rho from G to GLN A, such that the same thing, rho mod equals rho bar. And then you quotient now the following equivalence. That rho is equivalent to rho prime if you can find a G in the matrix, so invertible matrix. But not only I want it to be invertible matrix, I want it to be in some sense mod M. I want it to be the identity matrix. So I don't want to conjugate my original rho bar, but you can conjugate it after sort of the deforming part. You can conjugate such that rho is maybe rho x is equal to G rho prime x G prime for any x in G. Okay, so you can deform it after, right. So you can conjugate it after for the deformation part. So that, you see, when you conjugate here, you will not change the rho bar. So the rho modulo M is still rho bar itself. You don't conjugate the rho bar given to you. So somehow these two functors, in a sense that it characterizes all possible ways of deforming my rho bar into representation with coefficients in some complete Noetherian local ring. Maybe I should also say that this is also the same thing as free A module M of rank n with continuous A linear G action, and together with a G isomorphism M mod MM is isomorphic to V, where my V is this V here. So that's the same thing as sort of Galois action on a free A module. When I say Galois action on a free module, I have the freedom to choose the basis of the free module. So that amounts to the conjugation we have over here. But then I say, okay, the conjugation, you can't change things modulo M, so that's what this second part is. So I really want this M modulo MM is isomorphic to the V given to me. So that rigidifies it modulo M. So what is somehow, so let me state my theorem and then explain sort of the meaning it contains. Assume that my G is a profinite group satisfying the two star conditions. I mean, the two conditions are equivalent, so I just say star. So the first statement is that this frame deformation is represented it's representable basically. So it's represented by some object in the category. And secondly, if the endomorphism of Fg of rho bar is just F, then the unframed deformation is represented by okay. We'll take a break and then come back to the meaning of this statement. So where am I? Okay, so now let's explain the meaning of this representability. Just a tiny bit. Before proving it. So I left it here, so I want to start with a rho bar. I want to lift it. Now let me explain the meaning of A. Basically, what it say this function is represented means that there's a universal one. The way how it's set up is somehow on this ring, our row bar frame, there's universal representation. We write rho universal. Such that for any AM in the CL, a complete Noetherian local O algebra. I mean, for example, if you want to consider the lifting I just erased, you can take O and var pi, and so. But now I'm going to talk about sort of general situation for any such thing, and every representation rho from G to GLNA, lifting rho bar, in the sense we had over here. Hold on a sec. The way I grammated it somehow, for any A, and then every representation will comes from a unique ring homomorphism from R rho bar to phi, call it phi, from the R rho bar to A, such that the representation, I'm out of space here, so the representation your new representation you lifted, it's not something new, it's something already known, in the sense that we have this universal representation GLN of R rho bar framed, then apply this ring homomorphism. Of course, I get from GLN R rho bar framed to GLN of A, and that composition is your rho. So that's the meaning of the representability of this functor. It means that you have a universal one. Whenever you have any other any lift of rho bar, it's just obtained by composing this the usual representation with a homomorphism from the universal deformation ring to A. So a couple of names. So this rho bar is called universal frame deformation ring. And similarly for this one, just unframed. Or sometimes people don't say the word unframed, just means framed. Depending on the time we have today, I definitely will not prove B, but I'll try to finish part A. That's the goal. Okay. As I said, somehow the meaning is that somehow every representation really comes from the universal one. So in other words, let's phrase this in a more, I guess, categorical language. If I have an object, deformation frame A, that means that I have a continuous representation rho lifting my rho bar with coefficients in A. And that's the same thing. As I just described, that every such representation comes from a unique ring homomorphism from R rho bar frame to A. So that's just same thing as, so there's a bijection between this and the hom of R rho bar frame to A. Maybe to be precise, I'm taking hom in the category of complete Noetherian local O algebra. Okay? Or, if you want to say it in the sort of fancy language, this functor is the same as a functor that are the same functor. So that's the meaning of the representability. Let me also say a little bit about where this rho universal comes from this ecology of the functorial point of view. So this is some sort of Tanakian language. So whenever you have a functor equality like so, So you can apply it to the special case where A equals, or as you can say, take A equals to R row bar frame. So you just do, on this side, just put in R A equals here. So on the other side, you have the harm. I'm going to be lazy not to write the subscript here. So it replaces A by R row bar frame. So now on the right hand side, you have an identity homomorphism. By the equality, it will correspond to some object here. By definition, it's a function applied to this ring here. It means that it's a representation lifting the row bar with coefficient in R row bar frame. So this is precisely your row universal. So if you have a representable functor, if you apply the representative functor to the universal ring itself, then the identity on the right-hand side will correspond to the universal object on the left-hand side. That's a sort of general principle. So let me erase the second part. We're not going to prove it today. So the proof goes as follows. So we'll prove the first one, and really do the quotient by the action of the conjugation in some sense. We'll do that quotient next time. So let's focus on A. So first, let's do the case where G is finite. Let's say I could take all the elements in G, but anyhow. But let's sort of still take things with generators. So say G is generated by some number of elements. You can take all the elements in here if you want to. And satisfying all these relations. So this is relation 1 to relation T. This is completely abstract whatsoever. Then think about what is the representation of a representation of G means. It basically means that somehow assigning an invertible matrix, of course. Well, let me take it so that these relations contains the inverses. In the sense that if you have a G, originally if you write relations, automatically you assume that somehow whenever you write G, there's a G inverse automatically defined. So let's don't do that. Whenever you have it, let's double it. So whenever you do a G and G1 prime, over here you take the condition G1 is equals 1, and then you just put in these conditions. Okay? So let's do the condition without taking the inverses. You can represent a group like that. So therefore, I can simply say, okay, a representation of G is basically assigning just a matrix to each GI and satisfying the relations. That's basically what, that's just down to the earth what a representation means. For each G, you get a matrix. And then, of course, it satisfies all these relations you need. And then you get a homomorphism from G to GL, whatever. Right? So therefore, because of this, like think about how things could deform. I mean, I don't have to talk about deformation. I can just sort of simply think about just talk about all possible representations, not just deforming things. So what that really is, let me sort of rewrite what I just described. So I want to define a ring is a polynomial ring, R, with all these variables. The way I think of these variables, I really think of this sort of this is a kth element in the generator, and this is the ij entry of for each generator, I have a matrix. So this is the ijth entry of the matrix associated to the kth generator. Then I have to let's see, maybe give it. So whenever I have this, I will write x k for the matrix xij k. Okay? In the sense that I just basically put put xijk in the corresponding ijth entry of the matrix. Okay? Now I want to quotient now the following polynomial in substance. So relation 1, whatever that is, I do x1, xs minus sort of identity matrix of n by n matrix. When I write this, I mean that for each of the entry, I take the difference, or like, I mean to say 1, 1 entry minus 1, that's a relation. And the 1, 2 entry itself is a relation because over here is 0, and so on and so forth. RT of x1, xs minus I. So in some sense, I by hand put in these relations into the things you quotient out by. So I claim, I'm not going to prove this claim, but somehow, morally speaking, this R parameterizes all possible representations of G. Why is that? Well, let me not prove this because that's a very good question. But as I said, I want to put in the inverses here, so that all my relations are polynomial relations, including the ones that G1 times G1 prime equals 1. So automatically it's sort of inverted in some sense. Yeah. Yes. I agree with you. Yes. You could. We could put determinant inverted determinant. Either way. R is so for example, let me maybe give an example to say what it is. So I can't think of a. So let's see. So say G equals dihedral group. So R and S, right? What's this? Oh, so this is hold on a second. This is this, right? Right. So this is dihedral group, right? So let's talk about two-dimensional representations of this. So I want to take R to be O of so x1, 1, x1, 2, x2, 1, x maybe S. Excuse me. So x and 1. So x. Oh, my bad. xy, xy. Oh, I missed a condition. Sorry. So this is again x11, x12, x21, x22, and y11, y22. Now relations. So this is good. Relations. So let's write a couple of it. So for example, y squared equals 1. So that would mean that okay. I apologize. I can't think. So the relation is x11 squared plus x12 y21 equals 1. And then this, so x11, x12 times plus x21, x11 equals 0. And then, when you multiply the matrix itself, and there are four equalities here. And then this is even more complicated. There's no way you can write it down, but somehow you can write that. Yeah, good. So that's what I mean by this. So then, if I have a row bar, as I had earlier, from representation from G to F, so this can be lifted to a homomorphism from R to F, in the sense that you send this xij k to the ijth entry of rho bar of GK. Right? I mean, you can always send it to here. And then, of course, it's a polynomial quotient by something, right? And the thing you quotient now by is precisely because of the representation of G. So these relations will definitely go to 1. And therefore, these relations will somehow this map from the polynomial algebra to F will factor through these relations. So you will get a well-defined map from R to F as so. And you can imagine if you have another another ring valued representation, you can get an R to that ring by exactly the same definition. But now I'm talking about deformation of this rho bar. So I have to take the kernel of this. And my claim is that I want to complete of this R at this max. So this is the maximum ideal. At J. So let me call this one Rj completion represents the function. So I'm going to prove this claim. So proof. So I have a rho universal from G to GLR, sending a GK to Xij K. Remember that so G has some relations. I mean, if you want to have a homomorphism from G to some ring, you have to sort of specify what generator goes to, and then also this is a matrix. This is a matrix. Right, you have to specify where the generator goes to, and then checking the relation is met on the other side. But that's precisely what you quotient out by on this side. So you get a universal representation. And then, of course, because you completed, you can continue on to the completion. So this is a continuous group homomorphism lifting my given rho bar. Now, on the one hand, for any complete Noetherian local O algebra and any morphism incomplete Noetherian local algebra, it will give an induced representation. I mean, you just basically compose this universal one with the map from Rj hat to A. So basically, you just take G, use rho universal, goes to GLN of Rj hat, and then continue on to this. Now I have to do the converse ones. Converse one is the more difficult one. So conversely, given a rho A in here. So suppose that I have a lift of rho bar, a representation of G with coefficient A, then I can form a so-called rho tutor from R to A by sending Xij. So this is the generator of this R is a polynomial algebra quotient by some relations. I can send each of the generators to precisely what I did before, Ij's entry of rho A of GK. As before, because the relation you quotient out by are precisely what you need to do to give a group homomorphism. So therefore, this is a well-defined map. And also this, of course, maps down to this, the lifts the row bar we had earlier. Maybe call it row bar tilde in the usual way. Okay, so this at least gave me a map from R to A. It will send, so now we're in a situation that row tilde will send J, my maximum ideal of R, into the maximum ideal of A, because somehow, how should I put this? So elements in J under this, so elements in J in here under this row bar tilde map vanishes. So therefore, when it maps over here, it must live in the maximum ideal. So therefore, this row tilde will send the maximum ideal to this M. So it will induce the map between the completions. Will induce this a completion to A. And therefore, of course, that gives you the other direction of giving a homomorphism from Rj hat to A is somehow equivalent to give an element in here. So conclusion of Rj to A is equal to deformation. So therefore, we prove the representability of this functor when the group is finite. Maybe I just want to make a small comment here that somehow my proof suggests that not only somehow the deformation problem is representable, somehow we can even talk about the moduli space of all possible representations without giving a row bar. Maybe just sort of make a remark here. Maybe quickly give a remark here. So the way I think of this what's going on here is that somehow I like to think of in terms of schemes, not rings. So I have the spec R, which is somehow the universal one, and over that I have a row universal, right? And my row bar is a particular point on that. I mean, whenever I read this, I mean, this corresponds to an R map to F. It's row bar. Okay, F. Okay, so this, if you think of spec, so this is some sort of, I guess, is some sort of variety over Z over O, and this is a point on a special fiber. And what this sort of spec Rj hat means is that this is sort of the completion at the point defined by, in some sense. And if you somehow want to draw this sort of the picture here, think of this as a spec of O, and this is sort of the spec F. This is sort of the generic fiber. What was that again? E, right? And I have some sort of space, which is sort of like that. So this is my spec of this R. Right, on this special fiber, I'm taking a point here. And somehow the completion, you could think of it as some sort of local completion like so. Okay? So the deformation problem can be thought of as somehow universal one is that starting with this point and see what kind of point over here can reduce to this. In some sense, I'm taking sort of all the information in this light cone. And you see that every time you give a representation with coefficient O, would amount to choosing kind of a line inside of here. So this may be any O representation. That's my way of visualizing this. So if you have another representation, it might be congruent to that for a bit. So it might be congruent to that. So what happens is that the other representation might go along and think of it as a spec of F, and then the formal neighborhood will be spec of, like say ZL mod L to the square, L cube, and so on and so forth. The congruences can be understood as somehow that these two lines, how far they bifurcate. And maybe somehow it will go a bit longer so that they congruent a bit further for different rows. So it's for different lifts, row 1, row 2, and row 3, for example. So that's a way I kind of visualize this. I just thought it would be nice to kind of talk about it. Okay? Let's maybe go back. We only talked about the case where G is finite. So now in general, I want to write my G is profinite. So I want to write this as inverse limit over open normal subgroups HI and G. Because of inverse limit, let's assume I give myself a row bar to start with, which has finite image. So therefore, the kernel is also open. So may I assume that all HI is contained in the kernel of row. Okay. So that, maybe it's bigger parenthesis. It hasn't done yet. So that my row bar from G to GL and F induces, say, row I bar from G. Because HI is contained in the kernel, so I can factor it out. Okay. So the idea we're going to use is that we want to use a deformation ring for each of the G mod HI, or rather, deformation ring for row I bar to get the deformation ring for G frame. What we do. So for each I, get a universal pair. The deformation is called R. Already. Of the universal deformation ring, and it's a bit long, just a bit more. So this is maximum ideal. This is just GL and F, and this lifts the usual row bar I. Okay. So I have the universal deformation ring, and I have the universal deformation. Now I want to link different HIs together. If HI is a subgroup of HI, then I have this row I from G mod HI to this GLN of R, the universal deformation ring, right? But then I can think of it as, because I can first quotient by G by a smaller open compact subgroup, and then quotient by something a little bit bigger. So there's a natural map from G mod HJ to G mod HI. So therefore, I do get a representation. So I do get a representation of G mod HJ this way. On the other hand, my G mod HJ has itself a universal deformation ring. I guess, anyways, has its own sort of rho J universal, right? By the universality of this rho J, So this representation must come from this. So there exists a unique homomorphism from R rho I, J to R rho I by universal property of the deformation. So then now I can just define my R rho bar frame, rho universal, to be the inverse limit over all the i's of this deformation ring. And maybe at the same time, let's just take the inverse limit of the representation as well, with respect to these transition maps. Somehow the idea is that we sort of pool these informations together. So there are two tasks to do. First is that I want to show that this deformation ring does belong, this inverse limit does belong to this. So essentially I need to show Noetherian. I'm taking the inverse limit of sort of local rings and their local maps. So that shouldn't be a problem. And completion, I think, also not a problem. But the problem is a Noetherian condition. We'll do that, later. I'll kind of explain that, hopefully. And secondly, is I want to show that this does represent the functor I want it to represent. I may not have time to get to the first one, but I will see how much I do. So let me sort of, but even if I don't have time, let me sort of still say a little bit of this. As I said, so this is clearly a complete local ring. But I need to show it Noetherian. So to show it's Noetherian, I need to show that somehow it's maximal ideal modulo maximal ideal squared and var pi is finite. In the sense that somehow every complete local ring, it usually looks like some sort of power series ring quotient by something. I want to show the number of elements in the power series ring is finite. So this will imply eventually that this looks like O of some variables quotient by some ideal. And of course, we want the number of variables to be minimum. That's precisely the dimension of this guy. But we'll do that later. So for today, for now, let's just focus on 2. So 2 I'll prove in full generality. So I guess I'll say a bit of 1 later on. We'll argue as follows. So of course, as before, so of course, given given the morphism R rho bar frame to A of course I get a rho A that deforms rho bar. That's not a problem. But of course the question is how to go backwards. If I do have a representation, why does it come from a homomorphism from the universal one? So conversely, given a representation rho A from G to GLNA, lofting say, row bar. And I can consider for each number k, the reduction of this mod its maximum ideal is kth power. Okay. So I first sort of reduces the given representation mod its maximum ideal to the kth power. But one thing I want to notice, because A is Noetherian, if you model out it by its maximum ideal, its kth power, this is finite. This guy is finite. My residual field is also finite, so this is really truly finite. So therefore, the kernel of row A k is open. Now I can then talk about the inverse limit. So I can do. Then I can find an ik such that hik is contained in the kernel of this row A. Okay. And therefore this row AK factors through. So now I have a representation row AK from G mod this hik going to GLN A mod MK. Right? Now I have this universal game, right? Now I have a universal representation of this guy to GLN, what was it again? R row bar IK framed. Right? I have this universal representation. By universal property of this thing, so I have a unique map as so. So I have a unique sort of ring homomorphism from R row IK frame going to A mod MK. Now, I mean, like, moreover, you can easily check that somehow. Can I just do inverse limit? I mean, like, you have to check some compatibility, I guess. If you have a k plus 1 here, right, this maps to kmk, you have to do sort of R frame row bar ik, like so. I want to check this diagram commutes, which also follows from, which also follows from the universal property of this. And of course, another thing is when you construct this hik, you want it so that also I guess I want my hik to be always contained in all the hi1, hik minus 1, such and such, when you do the induction. So that you do have a map from this to here. But anyhow, you just take this hi to be decreasing. And by the exactly same universal property, you have this diagram commute. And therefore, when you take an inverse limit, you get a map from this thing to here for all k. Maybe we also take so that, I mean, like, just shrink a little further to make sure that the limit or the intersection of all the ik is 1. So that this limit is just R, just that. So therefore, I get a map from this to here. So that means if I have a representation, I can construct this sort of the homomorphism step by step and then take an inverse limit. I get this map from the universal deformation ring to A. Okay. So that proved the representability of the frame deformation. So the question is, this proof hasn't used the finiteness condition yet, which is used here in the first one. So the finiteness is used to show this is finite. So the result you get is a Noetherian ring. If you don't have to find this result, I think you still have this representability, but then this inverse limit, this will not be a Noetherian ring. Maybe other places, I'm not so sure. I mean, like, leaving the Noetherian world, I'm very nervous. Okay, I'll say a bit more about one in a bit. Not now. So there's a second part of the proposition. Where was it? Okay. About the unframed deformation. So let me sort of give you morally how it works, and I'll give the details next time. So because I should think of this sort of the deformation. Remember that the way things are defined is that this is equal to the frame deformation quotient now by the conjugation action. So maybe I should write adjoint action of 1 plus matrix gives me n makes my ideal of A. Okay? And to be more precise, the adjoint action actually factors through this quotient out by the scalar matrices. Of course, the scalar matrix doesn't really conjugate. So writing it in a completely sort of formal way, what we're seeing here is that this deformation functor is the frame deformation functor quotient out by the group. Somehow, if you have the matrix modulo the scalar matrix called PGLN. So we're doing the formal PGLN. So in the next lecture, I'll make sense of what I mean by quotient. So you do have this. This makes sense, actually. So therefore, you should expect that somehow your spec R rho bar frame non-frame is equal to scheme theoretically this. Maybe I should do spuff because things are formal. So next time I'll explain why this makes sense. Okay, I'll perform this quotient next time. Or rather, I'm not going to work in the sort of formal way, formal category. I'm just going to do the usual sort of affine schemes and stuff, rings, but not formal scheme. Anyway, somehow the argument sort of goes through the same way. I'll discuss this next time. Okay, any questions? Okay, now let's try to at least state to talk about the so-called tangent space. So this is the sort of quotient I wrote earlier, essentially. So in this lecture, I will frequently use this. Whenever I write epsilon, I really mean fx, where epsilon squared is 0. Okay? So this is a two-dimensional f vector space. But I think of it as a ring. Epsilon squared is 0. Okay? Okay. I don't know why I do this, but somehow it's obvious that you have this. Okay? It's obvious. Okay, then every time rho from G to GLN, if I have a f epsilon valued representation lifting rho bar, I can let me call this one GL of V F epsilon. Okay, I can tensor this V F L epsilon with this exact sequence I have over here. Then I would get sort of 0 goes to V F epsilon goes to V. Right? We've talked about this somehow, like a thing like this is an extension of V by V. So in a sense that giving a lift of your representation rho bar to ring of this coefficient is equivalent to give an extension of V with V in some sense. I'm now saying in a very precise way. So let's do that. And this epsilon, I mean, this f epsilon thing can be used in many places. You can solve that sort of infinitesimal deformation of your rho bar. So I guess already see some relation between the deformation of rho bar of f epsilon versus somehow the x1 of fg of vb. In your homework, I'm going to ask you to do this is the same thing as h1 of g of so-called R-joint representation of v. Let me explain what R-joint representation is. So R-joint representation is V tensor with V dual. V dual. Or rather, somehow it's a Hom as a vector space of V from V to V. The G, somehow, if you have a phi here, the G action goes as follows. So G of phi acting on a vector x in V will be defined to be phi of so it will be phi of G inverse x of G of that. So first G apply to x, and then apply phi, and then apply G. Sort of standard. So this carries in G action. Or you can check this equivalently. When you have sort of the rho, write your representation rho as GLN of f as so. So this is R joint rho is the representation of G on the matrix. So this is representation on the vectors, column vectors of over F. And R joint is the representation of G on the matrix as a F vector space, as G acting on a matrix is just given by rho G of M, rho G inverse. So that's the representation. So these are all equivalent to each other. In some sense, this rho G inverse corresponds to the G inverse inside. The rho G here corresponds to the G outside. So proposition first. There's a canonical isomorphism between maybe there are canonical isomorphisms. First is that the deformation, so M rho bar frame denotes the maximal ideal of the universal deformation ring. If you quotient out that by M rho bar frame squared var pi. So now anything you quotient by var pi becomes a F vector space. If you take the dual of that F vector space, that's the same thing as talking about this. G. And so let me just write one more line. So this is the same thing as the one cocycles of this. And we talk about this is finite, so this is sort of finite. So that essentially solved the problem, earlier Noetherian problem. Secondly, I mean, here's this somehow when. I guess I don't need the star condition. This is somehow makes sense, probably. I mean, somehow this part makes sense. And I guess, okay, I do need that. When G satisfies star. Okay, secondly, it's a representability condition. So endomorphism of F, this row bar is F. The same thing here works without the frame. And this is now, if you don't have the frame, then this becomes H1, truly H1. Okay, I'll talk about the proof of these next time.